The next lesson in Chapter 3 is 3.5. Perform basic matrix operations. This is a different take on systems of equations. The definition of a matrix is a system made of rows and columns. Let's take a look at two examples on the right. It says state the dimensions of each matrix. A matrix is defined by a capital letter. Therefore, our first matrix is called matrix A. When we define the dimensions of the matrix, we always go rows first, then columns. If we look at matrix A, there's 1, 2 rows. So we start with a 2. And then as we think vertical for columns, if you take a look at matrix A, again, there are 1, 2, 3 columns. That makes matrix A a 2 by 3 matrix. Again, we always do rows first, columns second, to define the dimensions of a given matrix. On the right, we have matrix B. Taking a look at the rows in matrix B, technically there's 1, 2, 3 rows, but then there's only one vertical column. Matrix B is a 3 by 1 matrix. Matrices are made up of elements. An element is defined as just one number in a matrix. We use the row and column kind of breakdown to determine the element we are looking for. On the right, it says determine each element. A12. It's technically not 12. As we look at this, remember it's always rows first, column second. So what this means is that we want row 1 in matrix A and then column 2. And we want to know what number is at that location. So if I circle row 1 and then I circle column 2, or the second column, the value that matches both of those descriptions is element 4. So A12 is 4, the number at that position. Now in the second one, we have B31. So that means row 3, column 1. So remember, the first number is the row. The second number is the column. Now row 3 puts us at the bottom. Column 1 puts us right in that only column that we have, which means our matching element for each of those where it overlaps is 7. All right, let's try the last one. I'm going to go ahead and erase what I wrote before in matrix A. We're going back to that one. Now this time they want us to find 32. So now row 3 and then column 2. So if we go to row 3, well, wait a minute. There is no row 3, is there? I've got row 1 and I've got row 2, but there's no row 3. And if that happens, if they give you a dimension value that isn't within your matrix, there isn't a solution possible. So no number possible. We really have to know which ones are the rows and which ones are the columns to make these work. If you have more than one matrix, that would be 2 matrices. Matrices are equal if all of your corresponding elements are the same. You must have the same rows and columns as well. And we can use equal matrices to solve for variables. If C equals D, notice those are both capital letters. That means matrix C is equal to matrix D. Solve for X and Y. Well, if C and D are equal to each other, we know that the matrix 12 and then 3x plus 2, and then rows in second row 0 and negative 14. All the elements in that matrix have to be equal to 12 and 23, negative 7y plus 3, and negative 14 in the other matrix. Now, if we look at each individual element, we've got row 1, column 1, 12 and 12. So those both already match, matching elements. But then when we have row 1, column 2, notice we have 3x plus 2 in one matrix, matrix C, and matching that should match the element in matrix D of 23. That would allow us to solve for x. This is just basic algebra now. I'm going to move 2 to the other side, giving us 3x is equal to 21. And then think about what we do to get x by itself. Divide both sides by 3. And x would equal 7. So there's one of our solutions. Then in that second row, we're still going to keep going. I have 0 in the first column, but negative 7y plus 3 in the second column. They have to be equal for the matrices to be equal. Therefore, 0 has to equal negative 7y plus 3. And again, it throws in another little slight algebra 1 concept for us. But now when we move 3 over, it's negative. 0 minus 3 is negative 3. And then when we divide by negative 7, we get a fraction answer. And it's likely that that's going to happen. 2 negatives make a positive though, therefore y equals 3/7. And then last but not least, we've got our row 2, column 2, that last element, and notice they're the same in both, so we don't have to do anything with those. When asked to add and subtract matrices, it's pretty easy to do as long as the first rule is in place. Matrices must have matching dimensions, and all you do then is combine corresponding elements, like the first row and first column with the first row and first column, and so on. Let's take a look at a couple of matrices over on the right. If you take a look at the directions, we need to cross off A and B. I have no idea why A and B are there. It says given matrix M and N, please add those in, perform each operation. So capital M is matrix M, and we have negative 3, 5, 2, 0. In this matrix, we have 2 rows and 2 columns. So it's a 2 by 2 matrix. For N, we have 6, 5 in the first row, negative 8 and 2 in the second row. Also a 2 by 2 matrix. The two matrices have matching dimensions. To add them, M plus N, we literally just add corresponding elements. I'm going to draw a bracket on the left, and for my first position, to get that first part, I'm just going to take the first element in M, the first element in N, and add them together. Negative 3 plus 6. Then we'll figure out that answer. Then I'm going to take the first row, second element, first row, second element, and add those. Dropping down to that second row, I'm going to take the first column element, the first column element, and just add them together. And then last but not least, second row, second column, second row, second column, add those together. And now we literally just finish this by combining those matching elements, or those corresponding elements, sorry. Negative 3 plus 6 is positive 3. 5 plus 5 is 10. In the second row, 2 plus negative 8 is negative 6, and then 0 plus 2 is 2. And that is your addition matrix for M plus N. I'd like you to go ahead and pause the video and then just reverse the order N plus M and see what happens. Notice when you add them in different orders, we end up with the same result. And this is a rule back from chapter 1. Adding is commutative, which means you can add in any order and get the same result. It's the subtraction at the end that's going to be order specific. So let's go ahead and take a look at M minus N. For M minus N, as we create our bracket, be careful with subtracting, everybody. I know that seems easy enough, but we just want to make sure that we're subtracting negatives and doing all those things in the right order. First element with first element, row 1, column 1, row 1, column 1 is going to be negative 3 minus 6. And then row 1, column 2, row 1, column 2, 5 minus 5. Second row, column 1, second row, column 1. That's going to be 2 minus negative 8. And then last but not least, second row, column 2, second row, column 2, 0 minus 2. And then all we want to do here is combine our corresponding elements. I keep saying matching. Corresponding elements. And we'll get negative 3 minus 6 is negative 9. 5 minus 5 is 0. Now in that bottom row, we have 2 minus negative 8, which becomes 2 plus 8, which is 10. And then 0 minus 2, which becomes negative 2. And that is our subtracted matrix solution for M minus N. The last part of the video lesson is about scalar multiplication. A scalar is going to be a number that's outside of the matrix, like it'll say over on the right 4 times A. And all it is a number that's multiplied to every element in a matrix. You can make the numbers bigger or smaller. They can be positive or negative. They can be integers or fractions. But whatever number is out in front of the letter that defines your matrix is the number that you multiply everything in the matrix by. Let's take a look at our last example on the right. It says determine 4a given a equals, in the first row, 2, negative 4, 6, and in the second row, negative 1, 0, 8. Now, as we think about the dimensions, it's important to practice this every time, everybody. So I notice that if I look across, there are 2 rows. So it's 2 first, and then there's 1, 2, 3 columns. This is a 2 by 3 matrix. Now, if there's a number 4 out in front, just going to get rid of all these little squiggles here, that means we're going to take 4 and multiply it to simply every element within that matrix. And this is a really big mess, so sorry it's taking so long. All right, so we're just going to take that 4 and multiply it to the 2, the negative 4, the 6, and then the negative 1, the 0, and the 8. It's really simple. So 4a will equal, in row 1, 2 times 4 is 8, negative 4 times 4 is negative 16, and 6 times 4 is 24. And then in row 2, negative 1 times 4 is negative 4, 0 times 4 is 0, and then 8 times 4, 32. And that's literally all you have to do to multiply by a scalar. And this ends our video lesson for 3.5.